Hello and welcome to this Chemistry World webinar. I'm Mariana Kneppers, Chemistry World Science Media Producer. In today's webinar, we will be discussing all about the life and times of Nobel laureate Walter Kohn, which is the subject of a newly released book by author and scientist Professor Sir David Clary. Now, onto some introductions. We are very excited to have David Clary joining us today. There's David there. David is an emeritus professor of chemistry at the University of Oxford and was the first chief scientific advisor to the Foreign Office from 2009 to 2013. Among his many academic achievements, he was knighted by Queen Elizabeth II in 2016 for his contributions to international science. And as we will hear today, he is also an accomplished author, recently publishing a trilogy of books on the theme of science and World War II. One of those books will, of course, be the focus of today's webinar. But for now, let's get things started with some poll questions. We have two polls for you today, just to see how familiar you all are with today's topics. So before this webinar, had you heard of Walter Kohn? So a simple yes, no, maybe for you all. Maybe you're familiar with his name. Maybe you've heard of his work during your education in chemistry. Maybe you're a history buff and you've come across his name that way. Or maybe you're a massive fan and you know everything about him. Whatever that may be, we want to hear from you. So go ahead and put your responses in. And it looks like everyone's responded. It's quite an even mix between yes and I have heard of him, but no, know him very well. That is fine. You're in the right place. You're going to hear a lot about Walter Kohn today. And we have one more question for you. The other main topic of today's discussion is DFT. Have you ever used DFT? And of course, by DFT, we are referring to density functional theory. This is the quantum mechanical modeling method used to investigate the electronic structure of atoms and molecules. And it was a massive development in theoretical chemistry and physics, shifting our thinking from wave function to electron density. It seems like lots of people are familiar. We have 75% saying yes. A couple of people saying I think so, but not certain. You'll be leaving with a much better understanding, I think, today. And some people who know have never used density functional theory. Well, again, you are in the right place. No matter who you are, there is something to gain from the webinar today. So we are now going to pass things along to David. I'll now invite him to join us on screen. David, you can go ahead and turn on your camera and microphone. There it is. We can see your PowerPoint, and now it's full screen. Fantastic. All right, well, I'll leave you to it, and I will see you all at the end of the presentation. Enjoy.
Thank you very much, Mariana. It's a great pleasure to be able to talk today about my new biography of Walter Kohn. Walter Kohn was one of the great scientists of the 20th century, and his achievements are really impacting the science and chemistry, molecular science we all do in the 21st century. And so I'm going to have the opportunity to tell you about him today. Now, a special feature of his story is that he had extraordinary challenges when he was a teenager that affected his life and affected his science. And that's going to be a main priority of what I'm going to tell you about today as part of his extraordinary story. Now, this is his CV, and I'm not going to go through all the details at this stage, but I will be treating most of these aspects with you. Born in 1923 in Vienna, in Austria, and then this extraordinary career, essentially as a physicist, but ending up with the Nobel Prize for Chemistry in 1998, jointly with John Popel. Now, this was Walter Kohn. He's the boy there on the left with his close sister Minna in his family in Vienna in 1932. His father wasn't a scientist. He had a postcard company with two brothers called Walter Kohn that was very successful at that time. And so Walter Kohn did grow up in a reasonably wealthy family in Vienna. And this is the school that he went to, the Akademische Gymnasium in Vienna, one of the very best schools. I visited there recently. There is in Vienna. And many famous people, especially scientists, went to that school. Boltzmann was a student at the school. Schrödinger was a student at the school. Lisa Meitner took her exams there, and so on. So Walter Kohn was very happy there. He was getting a very good education there until the age of 15. And then this happened. Probably the most dreadful day of Austria in the 20th century, what was called the Anschluss, when the German troops marched into Austria in March 1938. And this is a picture of Hitler when he arrived on the 14th of March in Vienna. And this caused so many problems for Walter Kohn and his family, because he came from a Jewish family. His father, somebody took over Walter Kohn's father's business. The rights of Jewish people were very quickly taken away in Austria, as were the rights of Jewish academics. And he was forced to leave his school, his very good school, suddenly at the age of 15. He managed, though, to go to another school, this one here on the left, called the Chas Gymnasium. And he had a teacher there, Emil Noel, who quite remarkably had once been an assistant to Einstein. And so Walter suddenly found himself being taught by one of Einstein's assistants at the age of 15. And this was a sort of lucky aspect of what happened to him. This is a picture of Walter Kohn. I got this from the family of one of his associates, Peter Newhouse, with his other students. 3 other students, apart from Walter Kohn in this picture, all became distinguished professors of chemistry. So it was a really good school. But the trouble is, this was 1938, and things were getting very difficult in Austria for young people like Walter Kohn from Jewish families. And then the British came up with a brilliant scheme called the kindertransport. And this was a way of getting children out of Germany, out of Austria, who had to leave from Jewish families, and taking them by train to England. And it was called the kindertransport. And it was remarkably successful. Over 10,000 children were brought to England by this method. And one of those was Walter Kohn. And he took just about the last possible train out of Vienna in August 1939 to Britain. And the war just started early in September 1939. So he only just managed to escape from Austria and come to this new country of Great Britain. And he stayed with a very caring family in Copthorne in Sussex. And he went to East Grinstead Grammar School, which was a good grammar school. He actually studied maths, physics, and a little bit of chemistry. He was doing the equivalent of what people in Britain now do called A-levels. And there's a very sympathetic headmaster there, Thomas Scott, who gave him these books on maths, these ones here, Maths and the Properties of Matter, that he kept throughout his life. So he managed, despite these difficulties, to continue his studying, at least for a few months. But then things got very complicated for him again, because in the summer of 1940, the German troops invaded countries like Belgium, the Netherlands, and eventually France. Things were very difficult in Great Britain, and Winston Churchill announced collar the lot. They had to arrest everybody who'd come from Germany and Austria and Czechoslovakia, even if they were Jewish and had decided to come to Britain. They were all arrested. So Walter Kohn was arrested and interned and was sent to the Isle of Man initially. And then he was sent on this boat here, the Sobieski, all the way across the Atlantic to Canada. It was a very dangerous time. Some of these ships that were sent at that time from Britain to Canada were torpedoed by the German U-boats. And apparently his boat was followed by a U-boat, but fortunately it wasn't hit. And he went to this internment camp in New Brunswick. in Canada, where it was very snowy in winter. The facilities were very primitive. This is a picture of him with some of the other students in the camp. I got this picture from this chap, Joseph Eisinger, who had his 100th birthday when I was doing this book, and gave me a lot of these photos that you're seeing today. And he also became a distinguished scientist. But there was another lucky aspect of Walter Kohn at this internment camp, because in the camp was Fritz Rothberger, who also came from Austria and was a very distinguished mathematician. And what Rothberger did, he gave almost individual tutorials to Walter Kohn in this camp on how to do fundamental mathematical proofs. And this gave a background to Walter Kohn in his studies that became very useful later on when he made his great discovery of density functional theory. So yet again, despite all these difficulties, there were special aspects which enabled him to continue his education and have some exceptional aspects in the education that were really beneficial to him. Not only that, through this education, he managed to pass the scholarship exam and go to the University of Toronto, where he went in 1941 in the middle of the war. And this very distinguished biologist, Bruno Mendel, took him into his own house. And Walter and Joseph Eisinger stayed in this attic at the top of this house in Toronto, and Walter was allowed to go to the University of Toronto. He wanted to study maths, physics, and chemistry, but the chemistry professor would not let him go into the chemistry department because he claimed they were doing secret work and they couldn't have somebody from Austria in a department doing secret work. So he didn't study chemistry, just maths and physics. And he was lucky again because one of his other teachers there, Leopold Infeld, also had published papers and even a book with Einstein. And so really, yet again, they had excellent teaching at the University of Toronto. And this chap, Alex Weinstein, was a mathematical physicist who taught Walter what's known as variational principles. Walter, though, joined the army. He wanted to go and fight in Europe that was going on at that time, but they wouldn't let him go because he was Jewish. And then in 1945, he had the really terrible news that his parents, both parents, his cousins who he was very close to, his uncles and aunts, and 5 teachers had all been murdered in the Holocaust. His parents actually were sent on the last train to Auschwitz. His cousins had forced to undertake slave labor in the Lodz ghetto, and they were murdered, as was that teacher, Emil Nohel, who I mentioned before. And this had a huge effect on Walter Kohn. After that, he promised himself he would do something really significant in science to honor his parents, his cousins, and his teachers. And with no doubt, that is something he absolutely did. And he studied very hard in Toronto. Even when he was in the army, he wrote a paper on variational principle for electrons in atoms, and that enabled him to get a scholarship to go to Harvard, the great university in the United States. So in 1946, Walter came to this, probably the best physics department, almost one of the very best in the world at that time. And he worked with Julian Schwinger, who won the Nobel Prize for his fundamental theories on quantum electrodynamics. He also did some teaching for John Van Vleck in solid state physics. 2 of his friends there were Phil Anderson, who eventually went on to win the Nobel Prize, and Kohn also published with Nico Blombergen, who went on to win the Nobel Prize, as did Schwinger and Van Vleck. So it was a terrific place for Kohn to do his PhD research. And he published 1 paper in his PhD, and this was it. Published, all of his papers were in the Physical Review, not in chemistry journals. the variational method in nuclear collision problems. When atoms collide, you can apply quantum mechanics and apply a variational method to actually enable you to follow the atoms and molecules as they collide with each other using quantum mechanics. And Kohn did this in this very fundamental and important paper on nuclear collision problems. And I have to just add here that we did a little bit of work in my own research group on this. I had a brilliant research student, David Mandelopoulos, working with me in the 1980s in Cambridge, where I was then, and I set him on to use this Kohn variational principle to do the scattering of atoms off surfaces. Well, he took a bit of time to do it, but when he went to do a postdoc in Texas, Mandelopoulos got it all working. And we published it here in the Journal of the Chemical Society, Faraday Transactions. So we were quite an early group contributing to Walter Kohn's scattering theory. But the thing that he really then got interested in was solid state theory. He went to see this guy, Ed Kreutz, who had worked with Oppenheimer on the Manhattan nuclear bomb project in America. And Kreutz said, well, we haven't got anybody teaching solid state theory. Would you like to become an assistant professor at the University of Pittsburgh in Carnegie Institute of Technology here in Pittsburgh in the United States? So that's where Walter Kohn went and started to do research and teaching on solid state theory that was just coming out as being very important in the United States at that time. And the reason for that was really driven by these guys here on the left, Shockley, Brattain, and Bardeen. They're the ones who developed the transistor and are the first to develop semiconductors in transistors. And that absolutely changed microelectronics and solid state theory. And not only that, Walter went to have an interview with Shockley at Bell Labs, and Shockley hired him as his theoretician because John Bardeen here had left to go to the University of Illinois, where he was going to win his second Nobel Prize. So then Walter was in the very best lab in the United States for solid state research in Bell Labs in the US. But he always hungered to go back to Europe. He'd lost his family, he's lost his cousins, and he always wanted to go and do some work in Europe. And he managed to do this by visiting several times the Institute of Niels Bohr in Copenhagen. This is a photograph of Niels Bohr's institute workers in 1951. There's Niels Bohr in the middle, and there is the young Walter Kohn. So he was interacting with the very best physicists in the world, Niels Bohr, Shockley, Schwinger, Van Vleck. He was right at the top of his field, was Walter Kohn at this time. And he was a very good collaborator with all these important different groups. Shockley set him on the project of looking at what happened to semiconductors if they were sent to, in spaceships to outer space, and if the cosmic rays would destroy them. And Walter did some theory on how ions interacted with semiconductors to see if they could be damaged in outer space. So it was quite an interesting project for him. So he was quite successful interacting with these big stars. And then in 1960, a new university was set up, the University of California, San Diego. And these two scientists, Roger Revelle and Keith Bruckner, very distinguished, one in oceanography, and Bruckner, a distinguished theoretical physicist, persuaded Walter to come as the second faculty member in the whole university to help start the University of California, San Diego. This is what it looked like. It was a big move for Walter Kohn to go from Pittsburgh all the way to San Diego to help start a new department there. But he always wanted to go back to Europe. He very much regretted, of course, what happened to his family. This here was some of his family in Vienna. His mother, Gittel, is here. And this was his uncle, Johnny, in 1920. And this is Uncle Johnny in Lyon, France, in 1960. And Walter used to go back to France with the main aim of seeing his Uncle Johnny. And he went and did this on an absolutely important visit that he had in 1963. He went to France to see his Uncle Johnny, and he managed at the same time to go and do a couple of months' work at the École Normale Supérieure in the lab of Philippe Nozière. And Philippe Nozière had a postdoc called Pierre Hohenberg, and he put Pierre Hohenberg and Walter Kohn in Paris on the same desk together. And Walter Kohn said to Hohenberg, you know, has anybody ever found out if the electron density, that is the probability of finding a particle in three-dimensional space, the electron density, is unique in a particular atom? And Hohenberg went and looked this up, and he said, well, nobody's worked on that. So they went and then published this paper, which had the fundamental proof in it, because Walter had learned how to do these fundamental mathematical proofs in the internment camp in Canada, and showed in this that the electron density is unique. And also, if you've got the exact electron density, it's a minimum for the system. So you can apply a variational principle and minimize the energy with respect to the electron density. And this was a really important fundamental paper, the first paper that Walter Kohn wrote on density functional theory, published in the Physical Review in 1964. But this was just a fundamental mathematical paper. How was that going to be useful for atoms and molecules and condensed phases? Well, Walter, this is the electron density for hydrogen. It's just a fairly simple three-dimensional mathematical function. And it doesn't depend on, it just depends on X, Y, and Z. Now, Kohn was very good at working with other individuals very intensively, as we've seen in that Hohenberg work, for example. And he had a postdoc, Lou Sham, who came from Cambridge and had written in Cambridge one of the first Hartree-Fock computer programs to do calculations on solids. And so he was the ideal person to come to Walter Kohn and see if he can write a computer program to do the first density functional theory calculations. And what they did in this very important paper, the famous Kohn-Sham paper, is they derived, using the variational principle of Hohenberg and Kohn, equations for helping you to determine the electron density. And this is a quote from their paper, though. They said, we do not expect an accurate description of chemical binding. They thought this might just be useful for solids. They didn't think it could be used to describe bonding in molecules. Well, they were proven by chemists to be wrong in that assumption. Now, one or two of you are probably theoretical chemists today, and so I've got just one slide with some equations on. And if those of you who don't like equations, don't worry, this won't last very long. This actually is the basic Kohn-Sham equation, looking just like Schrödinger's equation, with a wave function here or an orbital here, a kinetic energy operator and various terms in here. But the crucial quantity here is this term here called the exchange correlation energy. If that exchange correlation energy is exact, then this electron density that you can calculate from these orbitals is exact. So this is a way of getting at the electron density and getting the other key properties, energies, and other properties of atoms, molecules, and solids through this Schrödinger-like Kohn-Sham equations. And that's what they came up with. but you've got to know what this funny term is, the exchange correlation energy. Now, Kohn initially estimated this just from calculations that had been done on the electron gas and showed that's quite useful for understanding the properties of surfaces, but it wasn't really very accurate. And the big thing that happened here was the chemists came in. The theoretical chemists came into density functional theory. And in particular, this guy here, Bob Parr, who had been a colleague of Kohn at Carnegie Tech University. Parr there was in chemistry, Kohn in physics, but they got to know each other well. And Parr realized that Kohn was a brilliant theoretical physicist, and maybe this method of density functional theory, looking at the electron density, could be used for chemistry. And Kohn did a critical sabbatical in Cambridge in 1953, where he interacted closely with John Popel, who is also an important person in this story. Just behind them was my postdoctoral supervisor, R.K. Nisbet. So I like to have a link with this photograph that was done in my year of my birth in 1953. But Parr was a key player. What he did in this paper here is he got the correlation energy, the energy of interaction of electrons that have been calculated very accurately for 2 electron systems, and fitted it to that energy, the correlation energy functional that I described before. And so he obtained a formula for the correlation energy functional. And then also around that time, or a little bit later, Axel Becquet, on his own in the Queen's University in Ontario, started to worry about what happens to the electron density when electrons are far apart from each other. And you can use actually formal theory to improve these exchange correlation energies and add those into the functional forms that were being used for the exchange correlation energies. And so these two groups, the Parr and Becquet, then came up with a mathematical form for the exchange correlation energy that was much more accurate than before. And they found it could be used quite well to calculate the important properties in molecules. So suddenly, density functional theory became a really exciting topic for chemists and molecular scientists. And all this came to a head at a conference that was held in Menton in France on the Riviera in July 1991. I was fortunate enough to attend this conference organized by the International Academy of Quantum Molecular Sciences. And Axel Becquet, sadly, he passed away just over a month ago, then met John Popel at this conference, and they had a 3-hour long lunch in which Becquet persuaded Popel that it was very important to use density functional theory in calculations on molecules. Now, Popel had developed a computer program, one of the first there was, for doing general calculations on molecules called the Gaussian program, but he hadn't put density functional theory into that program, and Becquet persuaded him to do it. So all of you watching today, many of you will have been to conferences. Maybe you, in your lifetime, you'll be lucky enough to go to a conference like I did that truly changed the field. And this is what happened at this 7th International Conference on Quantum Chemistry. Because what Popel did straight away after the meeting was go away and put density functional theory into his Gaussian program. Within 1 year, he was publishing very seriously using the DFT to calculate geometries, properties, dipole moments, vibrational frequencies, and so on of molecules. And that was a very big development because people had the Gaussian code and now they could all start doing density functional calculations. By this time, Walter Kohn had moved from Santiago to the University of Santa Barbara, where he was the founding director of what's become a famous institute for theoretical physics. And this is a picture of it that I took, which is called Kohn Hall. after him. So he was in Santa Barbara on the 13th of October, 1998 at 5 o'clock, asleep in bed. His phone rang, his wife picked it up and passed it to him, and it was from a theoretical chemist, Björn Roos, who was a member of the Royal Swedish Academy of Sciences, and it turned out a member of the Nobel Committee for Chemistry in that year. And Roos said to Walter Kohn, "I need to emphasize that your Nobel Prize is in chemistry, not physics." And Walter Kohn replied, "Well, that to me makes it a lot more fun. I mean, it's hard enough for a physicist to get the Nobel Prize in physics, but to get it in chemistry is even a little bit more unusual." And here's a photograph of Walter with his wife just after he'd heard he'd won the Nobel Prize for Chemistry, and he'd only published one paper before in a chemistry journal. All of his previous papers were in physics journals, and yet he still won the Nobel Prize for his fundamental developments of DFT. And since that time, there's been a huge scientific revolution in using DFT for simulating molecules. It's now very widely used throughout chemistry for molecular structures, spectra, reaction paths, properties, new catalysts. It's used now throughout material sciences to see if you can predict new materials. It's used in drug discovery. It's used for new antibiotics. It's even used in geology to predict the temperature at the center of the Earth. And by this month, over 600,000 published papers have used Walter Kohn's DFT, and 12 DFT papers, including Kohn's 2 papers with Hohenberg and Sham, are ranked as the most highly cited 100 scientific papers of all time. And there's even been articles written about the citations of DFT. There's hardly anything else in modern science that is like it. It's quite extraordinary how this fundamental work came out of Walter Kohn, has really revolutionized computational chemistry, computational molecular science. And here's a few examples of this. This is a paper by Omar Yaki, who just won the Nobel Prize this year for work on metal organic frameworks. And he has been using DFT quite routinely now for the last 10 years or so in his group to calculate the properties of molecules. He mentions it here in this particular abstract on chiral molecules. So there's many, many examples like this. There was a paper just published last year of a new antibiotic in Science. And they, in this particular work, they did DFT calculations and many other experimental works. It's very useful to do the DFT to see what a molecule looks like that might be able to bind through the ribosome. And that's what they did in this particular work. So even in biology, DFT can calculate more complicated molecules, give you pictures of molecules, give you NMR spectra and other properties, and be a very useful technique. It's revolutionizing material science. You hardly can pick up a paper nowadays in material science that doesn't mention DFT. And not only that, because we've seen it's a fitting process that you have to use to get those exchange correlation functionals, it links very well with machine learning and artificial intelligence, where there's also been a scientific revolution. And this means you can perhaps fit a small number of functionals, DFT functionals, and then you can extrapolate those and use them with machine learning to do many more calculations. So it's linking beautifully with the modern field of artificial intelligence as well. Now, Walter Kohn, especially after he won the Nobel Prize, didn't stop there. He had a real conscience about the world. because of what happened to him when he was when he was a teenager back in Austria, he felt very strongly about some aspects. One of those was the use of atom bombs. And he wrote a letter here to the New York Times asking for a hydrogen bomb ban, which proved to be quite influential and was eventually done. And then he was also in the University of California, very annoyed. University of California managed the nuclear weapons lab in the United States, at Los Alamos and Livermore laboratories. And he was very much against this. He campaigned, even after he'd won the Nobel Prize, especially with the regents of the University of California. He said time and time again that a university shouldn't be running weapons labs. And in the end, they withdrew mainly from doing that at the University of California. So he had huge political conscience that Walter Kohn used to great effect. Now, 20 years ago, I became president, that's the head of Magdalen College in Oxford, and the first guest I had was Walter Kohn. He came to see me. I'd only just started the job. And the reason is that the great Erwin Schrödinger, who started wave mechanics theory, on which Kohn's theory is based, was a fellow at Magdalen College. And Walter wanted to come and discuss Schrödinger. It turned out he'd been to the same school as Schrödinger. It turned out both Kohn and Schrödinger had to escape from Austria in the late 1930s, and both came to England but didn't stay that long. So he had great deep links that he never met Schrödinger, but he had great deep links that he felt were there. And this is what he says about him. I have enormous admiration for Schrödinger. My own work is built on Schrödinger's work. It transforms it and it looks at it in a different perspective. I consider him as my scientific ancestor. Schrödinger's equation describes all aspects of the physical world we experience on Earth. Words like miraculous and preposterous come to mind. This was a statement from Walter Kohn. It's rather modest because he developed a really efficient computational method, essentially, for solving Schrödinger's equation. And if you want to know more about that, I've written the book Schrödinger in Oxford. That's a different story. And this is my book, Walter Kohn, From Kindertransport and Internment to DFT and the Nobel Prize, that you might well be interested in reading. And thank you very much for your attention.
Thank you so much for that presentation, David. I mean, what a fascinating individual. I do really love these webinars where we take a closer look at the person behind the science, behind the name that we see in the history books. It brings a relatability to light that we may otherwise struggle to grasp of these kind of big, larger than life names. It is really, really incredible. Now, we're going to go ahead and do two closing polls before we go into our Q&A, something that may spark a bit of discussion. So our first poll, should all chemistry students be taught how to do DFT calculations? What do you all think? Some of you may have done this in your own training and education. Do you think it's still relevant? Do you think with the advent of AI, for example, perhaps it may be outdated? Let us know what you think. And if you want to give us a reason why, go ahead and send that to us using your questions window. You can kind of elaborate a bit more there, and we can open this up into more of a discussion in the Q&A session. Now, it looks like everybody's answered. It seems 81% say yes, definitely. 19% say no, I don't think it's relevant to everyone. That's fair enough. Now, let's go move into our last poll, poll number 4. And this one I think will spark quite a lot of discussion. Walter Kohn never published in chemistry journals, as we said. But do you think it was right for him to win the Nobel Prize in chemistry? He's not really a chemist by training, but is that more of a function of not being allowed to pursue chemistry initially and having to pivot? I mean, does that make him any less of a chemist? But like I said, feel free to use the questions tab to elaborate on your answer. But it's looking like most people are saying that Yes, absolutely. It was still right for him to win the Nobel Prize in chemistry. Wow. So, David, what do you think of that last question in particular? Because to me, I would think, yeah, absolutely. I think it's such an overlapping theory. It overlaps. It's very multidisciplinary. But what are your thoughts on that?
I remember when he won the prize with John Popel, and there was a huge number of quantum chemists discussed it, and it was a very popular award because everybody knew how he had changed the field. Without Walter Kohn, there wouldn't have been DFT, and it wouldn't have had this huge effect that it's had eventually on chemistry. But other people, many other people contributed. Fortunately, well, they gave the Nobel Prize to two people, Kohn and Popel, but there were quite a few other people that I mentioned, people like Becquet and Parr, Purdue and others in America who really deserve something as well, but you can't give it to everybody.
Yeah, of course. I mean, you just have to look at this year's Nobel Prize winners. You know, we had it across three different people, three individuals, and it's it's just one of those things. As science progresses, science doesn't happen in a vacuum. It's very much a team effort, isn't it?
Yeah.
Yeah, absolutely. And why do you think it was that the Nobel Prize had been in chemistry and not physics? I mean, you had that really great quote from, who was it? Let me just pull up the name. Bjorn Roos, who said, I need to emphasize that it's in chemistry, not physics.
Yeah.
Well, do you know why it was in chemistry and not physics?
Well, as I've said, all of Walter's friends had won the Nobel Prize in physics. And he had been, I do know people who nominated him for the Nobel Prize in physics, and I do know people who nominated him in chemistry also. But the point is, it was the huge influence it had on chemistry. And there have been previous examples of that. You know, Ernest Rutherford, who first worked out the structure of the atom, the great experimental scientist from Cambridge in the UK, he actually was given the Nobel Prize in chemistry.
Oh, I see.
And in a way, that was a nice precedent. It almost makes it more interesting, more exciting, if you don't quite win it in the way that some people expected.
Yeah, definitely cause for a bit more conversation, isn't it?
Yeah.
Now, you had mentioned DFT now is used in things like drug discovery and other aspects of medical research. How is it used in medical research? Can you elaborate a bit on that?
Well, I can give you an example. One of my students has set up a company in San Diego, where Walter Kohn came from, in looking at how small molecules interact with biological molecules and calculating the energies of interactions. And you can do that very efficiently with density functional theory and also with combining it with machine learning. Machine learning needs lots of data that's provided by density functional theory, and it enables you to then predict thousands of different candidates for these ligands that might be able to be used, or candidates that might be able to be used in drug discovery. So that's become a really important area used by the big drug companies, pharmaceutical companies around the world now, that's come out really of quantum chemistry and density functional theory and machine learning.
Yeah, it's amazing. I mean, we've had quite a few different webinars, even in the past month, all about drug discovery. And the underlying thing is that DFT, that theory is, it may not be mentioned per se, but that is what's making all of these algorithms, work. That's quite a good segue into my next question. What is the role of artificial intelligence in all of this then? Do you think that AI eventually will make DFT redundant?
I don't think machine learning will make it redundant. And as I've explained, it's intricately linked to what you do in DFT, because what you need in machine learning is data. And you have to get that data from somewhere. Now, some of that data does come from very good quantum chemistry calculations, not just from DFT, but those are very expensive to perform on larger, more complicated systems like those you get in biochemistry, material science, and so on. So I think DFT will always have a role, It's also, DFT is very good at calculating geometries of molecules. You need that in all these different applications as well. So some of the aspects of DFT will be replaced by machine learning, but you'll always need the data that comes along with it.
Yeah, of course. We're still in a phase where, artificial intelligence is being fed by certain models. So, if you don't have that base thing to start from, I mean, it's still relevant, isn't it?
Yeah.
Now, we're talking about quite a theoretical physics, theoretical chemistry. It's only fitting to ask a bit of a theoretical question. If Walter Kohn had not been interned, theoretically, and sent to Canada in 1940, do you think he would have gone on to win the Nobel Prize?
It's a very good question. If Walter Kohn had not been sent to Canada, he was doing the equivalent of A-levels in a good school in Sussex. He probably would have passed those and gone on to study physics or maths at one of the British universities, I expect, at that time. Who knows where that would have led? And he was a very clever person. There's no doubt he would have done brilliant work. Whether he'd been lucky enough to have come up with DFT, I don't know. He might have come up with something else totally different. He always worked very well with other people. Nearly all his best papers were with one other theoretical physicist, like Hohenberg, like Sham. And so it was the key aspects of who he met and who he worked very intensively. So his whole career might have had a slightly different path. He probably would have been lucky to have won the Nobel Prize. You need a lot of luck to do that, and he had it.
Luck, right time, right place, right science. Yeah, there's a lot of factors, isn't there? Now, we have a question from the audience here from Mark. Mark says that his work had massive implications for chemistry, as we have mentioned. But what is the difference between a physical chemist and a chemical physicist?
It's a very good question, because I was editor for 20 years of the journal Chemical Physics Letters. And really, nowadays, I would say there is very little difference between the two. They both apply physical ideas, physical methods to chemical problems. Both of them do that. I think maybe in chemical physics, you sometimes used to get physicists publishing in journals, whereas in physical chemistry, you don't really get that at all. So it's more about the community of scientists, really, but the interactions between chemical physics and physical chemistry are now really very much blurred, I would say. It's a good question.
Yeah, it's an interesting one, isn't it? Is it just the terminology? Is it? But there are very, very minute differences, aren't there?
Yeah.
Now, you've been talking about Walter Kohn's life and his achievements, but you also mentioned that you actually met him and had the privilege of speaking with him in person. Can you tell us a bit of what that was like? Like, what was he like in person?
Walter Kohn was a very popular person. That's not always true with Nobel Prize winners, but he was. He was very interested in what people were doing. He was a very humane person. And it wasn't just about physics, as I said, it was about many other types of issues. A very pleasant person, and I met him several times after that as well. I met him at a conference in China, I remember, a few years after that. Very popular, and I don't know if that's always true with the very top scientists, the very top physicists. They always have their problems and quirks, but not with Walter Kohn. Really nice guy.
It's so nice to hear that, because there's always the saying, never meet your heroes, but I think people forget sometimes there are really lovely people that are your heroes out there, and to meet someone who's gone through as much as he has, and
he always, although he originally was a physicist, after the Nobel Prize, he very much appreciated the chemistry aspect, and he went to a lot of chemistry conferences. I remember meeting him a couple of times at meetings of the American Chemical Society that he used to go to. So I think he suddenly felt like he'd transferred into the quantum chemistry community. A lot of the quantum chemists knew him quite well. That was the group that really took his ideas forward and made them work, and he fully appreciated that.
Yeah, it is amazing because, you know, the thing that really stuck out to me was in the beginning of the presentation, you mentioned early on he wanted to get involved in chemistry. He wanted to pursue that as a path. And,
Yes.
you know, he wasn't allowed to
Yes.
for whatever reason. And so it's almost like a very roundabout way of eventually coming into chemistry. It's kind of like a nice full circle moment, isn't it?
Yeah, he never worked in a chemistry lab. When he won the prize, he got a very funny postcard that he sent to all his friends showing him a sketch working with test tubes and things like that. He'd never done it in his life. And there he was winning the Nobel Prize for chemistry.
But still very, very well deserved. I think we can all agree that.
Yeah.
Now, another question for you. Why have you chosen to focus specifically on scientists and World War II in your books? Is there something about those stories that you find particularly compelling?
It's a very good question. Well, my first book was on Schrödinger, and it turns out that he came to my college, Magdalen College in Oxford, on November the 9th, 1933, and immediately on that day heard he'd won the Nobel Prize himself in physics, in this case. And so I felt a very close link with Schrödinger and Schrödinger in Oxford. So I wrote my first book, was called Schrödinger in Oxford. And then I discovered one of his associates, close associates of Schrödinger, just disappeared in the Second World War. And I did a lot of research and discovered what happened to him, and then discovered there were quite a few other people like this person who disappeared, who were very brilliant scientists who disappeared, who'd actually wanted to come to Britain, like Walter Kohn did, and weren't able to. And so my second book was called The Lost Scientists of World War II. And after doing that, and after the fact that I'd known Walter Kohn quite well, there wasn't a full biography of him written. There was a very good article written about him by somebody called Andrew Zangwill in America, but not a full book, a biography. And so it was almost a natural for me, following on for those two other books, to finish the trilogy of 3 books about scientists and World War II.
Wow. And what's next for you? Do you have any other books that you're gearing up to write next, or are you taking a break, or what are you thinking?
I do have another book I've been working on. I have to say, I go to the archives to do these books. So Walter Kohn's archives are in the University of California, Santa Barbara. So I had to go and spend some time in Santa Barbara going through all the archives to get the material for my book. Recently, I've been to another archive, and it's a secret.
Oh, is it? Okay. We won't share anything, yes.
There'll be another book next year, which I think will be interesting, that's connected to these 3, but is a little bit different. And that's what I'm working hard on, those archives at the moment.
Oh, that's very exciting. I mean, you know, having to travel to Santa Barbara is no bad thing. I'm originally from California myself, and yeah, I know Santa Barbara very well. It's lovely, especially this time of year when it's cold in the UK. Another question from the audience here. It is from Raj. Raj asks, why are wave function-based methods not recognized in the same way as density functional theory? For example, the Nobel Prize was awarded for developments in DFT, but not for wave function-based methods, despite the significant advantage in wave function approaches. What accounts for this distinction in recognition?
It's a very good question. There have been previous Nobel Prizes for wave function theory, and John Popel's Nobel Prize wasn't just for DFT, it was for his contribution. Now, what happens in wave function theory is you have to worry about the interactions of all the electrons. Each electron has an X, Y, and Z coordinate. So if you've got 1,000 electrons, you've got 1,000 X, Ys, and Z coordinates. So those calculations, although they can be very accurate on small systems, are much harder to do and much more expensive. Density functional theory just depends on one X, Y, and Z. That's why it's so simple. But wave function theories are very important. because they give you very accurate results that you can test theories like density functional with. One of the problems is so many people have contributed to wave function theory. And I always think, I'm sometimes asked to nominate people for the Nobel Prize, and I always think, well, who in wave function theory should get it? And you can think of 20 or 30 names. And you've got to have this home run. You've got to have something that really stands out to win the Nobel Prize. Walter Kohn had that. The many contributors to wave function theory have done great work, but they haven't perhaps had that home run.
Yeah, perhaps there isn't that poignant point in history that said that is the turning point. Perhaps it was more of a gradual shift, and that exactly. It is quite difficult to be able to, quantify that and name one name or three names or two names. So I don't envy being in that position. I can imagine, if you've been consulted for a Nobel Prize nomination, my gosh, it's quite a big, steep responsibility. Now, I have one last question for you. We get a few viewers, well, quite a few viewers to our webinars that are at the early stage of their career as chemists. And it'd be interesting to hear from your personal experience. How did you get started in your own field? Or how did you get started with writing kind of chemistry stories? Do you have any advice for those wanting to follow a similar path?
Well, I did my PhD in Cambridge in fundamental quantum chemistry, trying to do accurate calculations on very small atoms and molecules. That's how I started. But the best advice, if you want to get into something like quantum chemistry, the best thing you can do as a young student is to do as much maths as possible. That's not just true in quantum chemistry, that's true in lots of other things nowadays. So that's my very first recommendation, is that when you're at school, when you're at university, try to do the mathematics courses. And then see if you can find a research group that's doing really exciting, cutting-edge research. If you want to have a career in quantum chemistry, like I did, you have to do a PhD in it. And I really got into the historical aspects because of Schrödinger. I'd spent my whole career, 40 years or more, trying to solve his equation. And then I went and he came and heard he'd won the Nobel Prize in the office where I worked in Magdalen College. And that got me really interested in history and science history. So it was almost a natural for me to start writing these history books linked to what my previous research had been about.
Yeah, it's just getting that next dimension. Once you focus something on a subject so much, it becomes a bit all-encompassing, doesn't it? You just want to know everything about it and the person behind the name. So, wow, really, really interesting to hear about Walter Kohn, but also about your own experience, David. So thank you so much for your time. And I'm afraid that's all the time we have today. But again, a massive thank you for spending the time and taking some time out of your day to chat with all of us about your new book. And thank you to Andrea and Valentina also, who have helped to organize this event. For those of you interested in purchasing, the book is the same title as this webinar, Walter Kohn, From Kindertransport and Internment to DFT and the Nobel Prize. We will share the link to purchase this book in the chat, or I think we may have already done that. You can get 25% off using the code WALTER25, that's all caps, no spaces. And thank you to my wonderful Chemistry World digital team, Ben Valsler and Chris Pink, who have been working behind the scenes to make sure that the event runs smoothly. Thank you all for joining us, and we hope to see you in another Chemistry World webinar soon. I'm Mariana Kneppers, Chemistry World Science Media Producer. Goodbye, and see you next time.
Thank you. Bye.